Let's talk about one of the biggest scientific puzzles of all time. A puzzle that, according to the math, should be impossible to solve. But here's the thing. Nature solves it constantly inside every living thing on this planet. So what is this insane puzzle? It's all about proteins. You know, these tiny little machines that basically run our bodies. For a protein to work, it has to fold itself into a very specific, very precise 3D shape. And the question that haunted scientists for 50 years was, how does it find that one perfect shape out of an almost infinite number of wrong ones? And this is where things get kind of mind-bending. It's a concept called Levinthal's paradox. Back in the 60s, a biologist named Cyrus Levinthal did the math and had this shocking realization. If a protein just tried to find its correct shape by randomly testing every single possibility, it would take, well, literally longer than the universe has existed. Just look at that number. That's the number of possible shapes for just one small protein. To put that in perspective, that's more than the number of atoms in the entire known universe. So trying to search through all of those options one by one, it's not just impossible, it's cosmically impossible. And this right here, this is the paradox in a nutshell. A random search would take trillions upon trillions of years, but in your body right now, proteins are snapping into their perfect shape in milliseconds, in the blink of an eye. Clearly, nature has a shortcut, and for half a century, the big question was, could we ever figure it out? For about 50 years, our only way to even glimpse these protein shapes was through pure brute force. It was an era of slow, incredibly expensive, and just painstaking lab work. You could call it the dark ages of protein science. This quote is about the pioneers, Max Perutz and John Kendrew. In the 1950s, they spent over 20 years of their lives just to solve the structures of the very first proteins. It won them a Nobel Prize, sure, but think about that pace, 2 decades for one answer. These were the main tools in the toolkit, things like X-ray crystallography and cryo-EM. And they're amazing technologies, don't get me wrong, but they are so slow and expensive. It was totally normal for a PhD student to spend their entire 5-year program trying to map out the structure of just one single protein. That was the reality. And then in 2020, at what's basically the Olympics of protein folding, everything changed. A biological earthquake hit. An AI company, a company known for playing games like chess and Go, just walked in and basically solved this 50-year-old grand challenge of biology. The setting was the 14th CASP competition. It's this blind test where all these top labs try to predict the structure of proteins that have been solved but haven't been published yet. So nobody can cheat. And the results in 2020, they were just off the charts. I mean, this chart says it all. AlphaFold 2 didn't just win, it was a total quantum leap. See, a score over 90 is considered so good, it's basically the same as getting the answer from a physical lab. AlphaFold hit 92.4, and the next best team, they were way, way back at 75. It just sent a shockwave through the entire scientific world. Don't just take my word for it. Nobel laureate Venki Ramakrishnan put it perfectly. He said this happened decades before many people in the field would have predicted. The impossible problem was suddenly possible. So, how on earth did an AI do this? How did it find nature's secret shortcut? Well, the answer is just so elegant. It stopped treating biology like a physics problem and started treating it like a language. You've heard of ChatGPT, right? Well, AlphaFold 2 is built on the same fundamental idea, a transformer. It takes that long string of amino acids, the basic code of a protein, and reads it like a sentence. It learns the grammar, it learns which words relate to each other, and from that, it predicts the 3D meaning of the whole sentence. The key concept here is called attention. The AI is smart. It figures out which amino acids need to be near each other in the final 3D shape, even if they're really far apart in that initial flat sequence. It's like putting together a giant jigsaw puzzle by first finding all the edge pieces that connect, then building small sections, and then seeing how those sections fit together to make the final picture. And of course, the revolution didn't stop there. The next version, AlphaFold 3, widened its scope from just proteins to pretty much all the molecules of life. And it added a new trick, a diffusion model. It's kind of like those AI image generators. It starts with just a random cloud of atoms, and then step by step, it refines and sculpts that cloud into a perfect, accurate structure. Okay, This is the real paradigm shift. We're now moving from just being able to read the language of biology to actually starting to write it. This is the beginning of designing drugs from the ground up, right on a computer. So what does this new toolkit let us model? Well, it's the whole shebang. Proteins, sure, but now also DNA, RNA, and those little molecules that make up most medicines, all interacting with each other in one big system. It can predict with incredible accuracy exactly how a new drug might attach to a protein. And the implications here are just staggering. Like the folks at Isomorphic Labs said, what used to take years of work in a wet lab can now be predicted in seconds on a computer. That speed means scientists can test out thousands of potential new medicines virtually, exploring ideas that would have been impossible just a few years ago. So what does this all mean? The big takeaway is this. The very nature of discovering medicine is changing right before our eyes. We're moving away from an age of luck and accidental discovery to an era of intentional, rational design. We are learning to engineer medicines like we engineer software. Biology is literally turning into information technology. And the question isn't if we can cure diseases anymore, but how fast we can write the code to do it.